So, hello everybody. My name is Ilias. I've been working at the EBI for the past 7 years, and I'm a member of the ensemble regulation team since 2015. So, together today, we're gonna take a look into ChIP-seq. We're gonna do a ChIP-seq practical. We're gonna get actual hands-on practice, and let's see how it goes. Of course, for this presentation, I had the help of my colleagues, Garth and Davids, and I think we're good to go. Okay, what are the objectives for today's course? So after following this course, you should familiarize with ChIP-seq data analysis workflow. You'll get the chance to call actual picks from actual alignments. And you're also going to get the chance to visualize the output so it doesn't look boring as flat files usually look, but it's going to look a lot more interesting on a genome browser. And just to remind you that I cannot see your faces, so please interrupt me at any time with your voice. Otherwise, I won't be able to pick up any kind of problems or questions you may have. So all the data that we are going to use for today's practical can be found on your virtual machine under this directory. All the tools that we are going to use, except the genome browser, are hosted in Thomas's Docker Hub account. And after the training ends, you are going to be able to find this presentation plus a couple other files in this GitHub repository. As Puran has already presented yesterday, we are going to use this figure from a zebrafish publication. So it comes from the widespread enhancer dememorization and promoter priming during parental to zygotic transition publication. This is going to be our guide. We are going to use data that have been generated by the scientists in the publication, and we are going to try to, in a way, replicate their findings, obviously not the entire publication's findings, but we are going to try to get tracks that look like this. In particular, in this demonstration, we are going to work with H3K4 trimethylation from sperm. It's highlighted here with a green arrow, but inside your data directory in your virtual machine, there is data for H3K27 acetylation for sperm and oocyte as well. So you're going to have the chance to work on all three data sets. There are some distinct patterns that are described in this figure, and in particular, the H3K27 acetylation peak in this region. Are you able to see my mouse pointer?
Yes.
Yes.
Okay, great. So this H3K27 acetylation peak in sperm is not present in oocyte, and here in chromosome 19, there is a peak in H3K27 acetylation oocyte that is not present on sperm. Moving along, so I don't want to scare you. Probably several of you are already familiar with general ChIP-seq data analysis workflow. Something similar was presented yesterday by Puran as well. So this is not a strict workflow. There is room for some flexibility. This is more or less what we use in Ensemble for processing our data sets, and this is what we are going to use for processing AQUA-FAANG data sets. So here in the center, you see the main steps of the workflow. And here in these dotted boxes, you see the most popular tools for each step. And here at the very bottom, you get a sense of the files that are involved in every step. So as soon as the sequencing ends, we get our hands on the read files. So these are fast, the format for this read file is a FASTQ, and it more or less contains the reads that the sequencer has generated. And then after some QC, there is the alignment step, where we get to align our reads onto a reference genome. And after some sort of post-processing, like deduplication, sorting, and things like that, we reach the peak calling step, where we use a peak caller that will determine the boundaries of the enriched signal regions. And then the output of this peak caller can be either processed further on, as Malcolm will tell you in the next session, and can also be visualized with several genome browsers. So let's take a look into every step of this. So in the beginning, there's going to be the early steps are going to be hands-off for you. But after the middle point of this workflow, you are going to get like a hands-on with our data. So yeah, as I said earlier, our starting point are read files. So this is the output of the sequencing process. Usually, scientists publish their read files onto public archives like SRA or the ENA. This is how we also retrieved the data sets from the publication. I don't want to bother you too much with formats. So probably most of you are already familiar with most of them. So this is how a FASTQ file looks like. Every entry is consisted of 4 lines. The first one is a sequence identifier, and it begins with this symbol. Then we get the actual raw sequence. Then there is like a third line that begins with a plus sign, and it's optionally followed by the sequence identifier again. And then we have a fourth line that is like an encoded representation of the quality values for each base code. So usually these entries are found inside FASTQ files, like lots of them, one after the other, like this. And usually when you have paired and experiments, you get 2 files, like the forward and the reverse reads are separated on 2 different files. Yeah, it would be great if things worked perfectly with sequencing, but unfortunately, the reads that get out are not perfect. That's why we've got QC that determine the quality of our reads after the sequencing ends. So the most popular tool for QC after the sequencing step is called FastQC, and it actually is a set of several metrics. So now I'm gonna step out of the presentation, because the images that you see here come from a very nicely formatted HTML document. You can also find this document in the living Google document that Thomas and the rest of the training team has provided. So this is how it looks like. So this HTML document here contains the QC tools that we have used in our analysis. Here on the left-hand side, we're going to select the fast QC because this is what follows after sequencing. And here we get like all sorts of interesting stuff, and they are interactive. So it's a very nice way for a scientist to explore the quality of the data. So here, for example, we can see the proportion of unique reads to duplicate reads. We can see histograms that describe the quality of our read per position. And we can get like quality scores per sequence and all sorts of interesting metrics, JC content. And yeah, you probably are familiar with most of them, duplication level, adapter content. So instead of looking into boring files, text files, this multi-QC tool lets you aggregate and present your QC in a very, very nice way. I'm going back to the presentation now. So after this QC step, we move on to the alignment. So just a very, very general overview of what the alignment is about. So we have our set of reads that have been generated by the sequencer, but we don't really know where these reads come from. We know that we have a reference genome, and with the help of this reference genome and tools that are called aligners, we are gonna map those reads onto the reference genome and stitch them together, if that's possible. So most of the most popular um, aligners are BWA and Bowtie. The researchers in the publications have used Bowtie in their analysis, but in our own processing of their datasets, we have used BWA. And yep, I'm gonna move on. Similar to the post sequencing QC. Oh, yeah, before going to QC, yes. The output of the uh, um, alignment process is a BAM file. So a BAM file is a binary compressed representation of a tab delimited file called SUM. Some files can be quite complex. For our purposes now, you should focus on the columns that I have here in bold. So the first column is the query template name. The third one is the region where the read has been mapped on. And the fourth one is the start coordinate of that mapping. Column number 5 is also very important, mapping quality. All of them are actually important, but we are not going to take a look into all of them. It's 1, 3, and 4 that's going to be used in this hands-on practice. And yeah, as I said previously, more QC follows the alignment step, and the most prominent, the most popular tool for post-alignment QC is called SumTools. SumTools is like a jack for everything. I'm gonna go back to the HTML page. So here on the left-hand side, we click on the SumTools, and we also get like interesting stuff. So we get like the proportion here of reads that have been mapped onto the reference genome and the proportion of the reads that have not been mapped. You can actually see raw numbers or percentages. this page is very interactive. Yeah. And here there is also another table with several metrics. And for each metric, you get 2 dots because we had like 2 samples, 2 replicates. And yeah, you can hope you can see that it's quite easy to follow. And I'm going back to the presentation. Yep. Another tool for that offers nice quality checks for post alignment is Picard, and it has like a very nice breakdown of the duplicate and non and unique reads. So I'm gonna use this chance in order to talk a bit about duplicate reads. So after the alignment step, we see that there are several reads that have the same start position, and these reads are considered duplicates. So we cannot ignore those reads. Actually, since we are sequencing a very small, in ChIP-seq experiments, we are sequencing a very small part of the genome, some level of duplication is more or less expected. So we do not worry about the good duplicates so much. What we really want to filter out are the bad duplicates. So these are artifacts that are generated by overamplification of usually low starting material. And you can usually detect them because they stack up perfectly onto the reference genome, whereas reads in good quality peaks stack with overlap themselves and they have some sort of offset. They do not stack as perfectly as the bad duplicates. So there are tools for removing your duplicates from your BAM files. But in this tutorial, we are going to use generates as our pick caller. And actually, generates can remove those duplicates on the fly. So there is no need for us to have a separate step. Generates will take care of this during the pick calling. So yeah, enough with the talking. Now it's time for you to log into your virtual machines. And I'm gonna explain a little bit of how our data is structured and what you need to pay attention to. So inside this home directory, you're gonna find 3 different data sets. The first one is for sperm H3K4 trimethylation. The other 2 is for sperm H3K27 acetylation and oocyte H3K27 acetylation. So in this demo, we are going to use sperm H3K4 trimethylation, and there are 2 subdirectories. The first one is called ROI, which stands for regions of interest, and contains only reads that are mapped on our regions of interest. I have forgot to tell you. I'm going back to the publication. So these 2 regions that are displayed here come from chromosome 21 and chromosome 19. So going back to the data, inside this region of interest directory, you are going to find read files that are mapped only on these 2 regions, chromosome 19 and chromosome 21. This has, the reason for this is that we want to avoid long run times. The full data sets can be found under the full directory, where this directory contains all reads mapped across the entire reference genome of zebrafish. But I would advise against using them in this tutorial because your run times are going to be long. They are not unreasonably long for a regular work day, but they are too long for a course. Yeah, and also you can find the alignments that come from the publication in a separate directory here. Have you all been able to log into your virtual machines and locate this data directory? No answer means no for me.
I got it.
Okay.
It's okay.
Me too.
Yeah, me too.
Okay.
Okay.
So, yep, I'm gonna switch between the presentation and my virtual machine as well. So the first step that we are gonna do in this analysis is sorting. So we have already aligned the raw FASTQ files onto the zebrafish reference genome, and we have generated the BAM files for our regions of interest. But these BAM files are not sorted the way our pig caller expects them to be sorted. So for that reason, we need to resort them, and we need to sort them by read name. This is, if I go back to the SAM specification, the read name is the first column. The files as they are now are sorted by location. So let's try to sort our files by query name. For this purpose, we are going to use SAM tools sort. It is bundled inside a Docker container, but I hope that by just copy and pasting the following commands, you're going to be able to follow me in my tutorial. So our input files are these ones here, and we expect to have this sort of output files after the end of this process. Here are the explanation of the parameters that I'm using, but below here there should be a link to the full documentation for this tool. So if you want to explore more, or if you want more details, feel free to go directly to the documentation page. So yeah, I don't want to scare you with Docker, but like Docker is a very nice way to bundle all the dependencies that a certain software may have in one package. And it makes it very easy for us to consistently reproduce our pipelines when we move from one environment or one platform to another. So as many have people said yesterday, you can consider it as a bubble. Unfortunately, this bubble doesn't have direct access to the file system. That's why we need to use this mount option here. And in order to keep it short, I have created these two variables. The first one contains the location of our datasets, and it tells Docker, oh, here is where you need to look for the actual data. And yeah, this has to be bound during execution. So I hope that just by copy and pasting these three commands into your terminal, you'll have no problems whatsoever to follow me. So here the parameters that I'm going to use for sorting is -n, which tells to the tool that we need to sort the BAM file by read name. -o specifies the output file. And then we have here the number of threads that should be used and the required memory per thread. I'm going to jump into my virtual machine. I'm going to open a terminal. Okay. Is the font size good enough? Is it too big, too small?
It's good for me.
It's good. Yeah.
Okay, so I've moved into the working directory, into the data directory for spermates 3K4 trimethylation. Please follow along on your own virtual machine. So I'm gonna export the first variable and copy it and paste it